Hello, everybody. Thank you very much for being again here in the seminar series 2020. I would also like to acknowledge the traditional owners of the land and waters in which we work and live here in the center in Townsville, the Bindan and Wulgarugaba people, and honor their elders past, present, and emerging.
It's my great pleasure to be able to introduce Katharina today, and I feel very lucky because I have had the pleasure of working with Katharina on some amazing adventures up in Papua New Guinea, investigating some of the underwater CO2 seeps, and just getting to be on board a research vessel with her for extended periods of time. And so it's a great honor for me to have already worked with her, and I'm really excited to hear a little bit more about what you've been up to lately, Katharina. But for those of you who don't know, Katharina is one of the amazing researchers at AIMS, team leader for cumulative impacts, and has spent over 30 years researching coral reefs. She received her PhD from the University of Munich in '95, and has really been focusing her research on understanding the effects of anthropogenic disturbances on various ecological processes in coral reefs. So without further ado, I would like to present Katharina to talk about ocean acidification on the GBR, and the future is now.
Yeah, thanks everybody for giving me the opportunity to speak about a topic that I feel very passionate about, and that is still largely overlooked in the public debate about the changes of, in the marine environment that we are experiencing. So as Jody said, I've been working on ocean acidification in the Papua New Guinea seeps for about 10 years. But in the last few years, we have been trying to translate the findings from these CO2 seeps to processes that are happening on the Great Barrier Reef. So, the outline of my talk is I'll be talking about rates of ocean acidification on the Great Barrier Reef, as we've been analyzing in the last few months. I'm talking about the effects of ocean acidification on Great Barrier Reef coral reefs as we understand today. And I give you a little bit of a longer term outlook over the future of the Great Barrier Reef, just in the context of ocean acidification, disregarding warming, which is obviously also hugely important. So just for those people who have been less familiar with the ocean acidification literature, a very brief OA 101. The background is that we, as we all know, we're presently emitting about 40 gigatons of CO2 every year into the atmosphere. About a quarter of that atmospheric CO2 is entering into the ocean to create better equilibrium. That's about 9 gigatons per year. And seawater together with CO2 forms a weak acid, which is called carbonic acid. It means there's slightly more protein ions in the water, and the carbonate saturation state declines. Now, both pH as well as carbonate saturation, as well as some other properties in the seawater that are shifting with the uptake of CO2, are hugely important for the physiology and ecology of marine environments. And just as a quick reminder, really since the year 2000, the CO2 emissions have increased by as much as 30%. So we are still seeing, despite all political talks, very, very rapid increases. And the ocean is not yet in equilibrium. That means what's in the atmosphere is not yet all taken up, and changes will continue to occur. Now, warming is obviously one of the effects of having atmospheric CO2 increasing. Other greenhouse gases, such as methane, are not contributing to ocean acidification. So we are really talking about a CO2 effect, not a greenhouse gas effect in this case. Now, ocean acidification is relatively well predicted at large scales for open oceans. It's pretty amazing. People only really started researching the whole OA concept over the last 20 years, although it has been known since about 1960 that it may happen. So in the past few years, the knowledge has increased rapidly, but most of the existing data are from open oceans, where ocean acidification is following pretty much what's happening in the atmosphere, as well as some physiological and physical changes. But just to note on this map on the left-hand corner, which shows the changes in aragonite saturation state in the ocean surface, the area east of Australia is really one of the fastest changing regions in the tropics. And that's in absolute terms, not in relative terms. The Arctic oceans and the Antarctic are of great concern, as well as some open water bodies. But really on the eastern coast of the Great Barrier Reef, we do have a problem that is pretty much overlooked still. Once you zoom in closer, you see how complex the situation is closer to the coast. Acidification is not only a function of atmospheric CO2, but also of all sorts of processes such as currents, temperatures, salinity, nutrients, physiological activities such as photosynthesis, removing CO2, respiration, increasing CO2. And therefore, things like eutrophication, river runoff, upwelling, they're all contributing to a much more complex picture for acidification processes in the coastal waters compared to offshore. So all this together, all these various processes that are playing together mean that global ocean acidification models are typically not representative to what's happening along the coast. But from all the lab experiments and from field studies, we know that OA is a really important issue in particular for carbonate systems like coral reefs. And so what I wanted to do is understand how are the rates of ocean acidification measurably changing in a system like the GBR. What you're seeing on the right here is a modeled model output from the e-reefs model, and you can see the wild dynamics. But this model is still relatively young. It's purely forced by physics, and so we did take advantage of data to confirm and validate these models and see what is really happening in the world. So I used two data sets. One is the Heron Island CO2 acidification mooring run by CSIRO and financed by IMOS. And the whole thing really was a collaboration with Bronte Tilbrook, Joyce Smith, my postdoc, Craig Neal, and Eric van Orgen from CSIRO. So, and a lot of oceanographers and people from CSIRO and EMS have contributed to collecting these data on since 2009 on a regular basis. So at Heron, it's a buoy. It's one of those NOAA acidification buoys, equipped with instruments that sample CO2 both in the atmosphere and in the seawater every 3 hours, and also measure temperature and salinity. So the nice thing is it's measuring day and night. It's measuring in all weather conditions. But it is really only measuring in the upper ½ meter depth. The other feature of this station is that it's directly near coral reefs. You see the Mistari Reef in the background, so it's in the channel between Heron Island and Mistari Island. And it's in relatively clear water, 60 kilometers offshore, and so relatively near the edge of the continental shelf. The second data source I could find was from the Yongala wreck, again an IMOS station, one of the IMOS national reference stations, which IMOS is operating all around Australia. Data exists since 2009 in that AIMS is going out once a month to take seawater samples through bottle samples. Obviously, these samples are only taken during the day and typically in relatively calm conditions. But additionally to CO2, we are getting data on total alkalinity, dissolved organic carbon, nutrients, and there are a whole heap of instruments on that mooring that sample temperature, salinity from different depths. So these samples are taken from 4 different depths, average 10, 20, and 26 meters. The location of the Yongala is relatively coastal, so it's very close to the Burdekin River. It's in shallow, turbid waters, and obviously strongly influenced by river processes as well as what's happening in the GBR lagoon. And it is about 650 kilometers further north to the GBR. Now, from the Yangala, we don't have surface atmospheric data, but AIMS has been measuring. AIMS is one of those worldwide facilitated, accredited greenhouse gas reference stations, and we've been sampling atmospheric CO2 samples in flasks monthly since 1991. So that data source is also available. Now, what do these data tell us? First of all, obviously CO2 is going up in the atmosphere. These are the southern GBR data, and from the mooring, CO2 is going up as everywhere in the world on a regular basis, at a rate of about 2 parts per million per year. There's relatively weak seasonality, so the black data are winter, the red data are summer, and the trend is relatively well predicted by a linear function at this stage. Fugacity of CO2 in the seawater is also going up at the slope very similar, statistically not different from the atmospheric slope. But on top of that decadal trend, and I should say that these data from 2009 to 2019, on top of this decadal trend, you're seeing very strong seasonal fluctuations in agreement with temperature fluctuations. And you also see some erratic pattern in salinity, with obviously some very strong rainfall events and river flows affecting salinity throughout the time. There is an apparent increase in salinity, but it is statistically not significant. So on average, obviously FCO2 is higher in summer than in winter by about 50 parts per million. And we are also seeing on average a slightly higher signal at Heron Island at night due to respiration than during the day where photosynthesis reigns. So both in winter and in summer, there are significant differences between day and night. But the overall differences very strongly are really between winter and summer. Nevertheless, if you look at individual daily ranges, you're seeing that seawater CO2 actually fluctuates quite widely. So in summer, we're getting a mean dial range of about 45 parts per microatmospheres, but they can be as high as over 100. And in summer, that rate is about half that. So, sorry, in winter. In winter, the values are about 25 to 20 microatmospheres. In summer, they're more like 45 on average. So big fluctuations that are happening on top of the seasonal fluctuations that are happening on top of on the decadal trend. Now we know that there are temperature and other drivers for the fugacity of carbon dioxide. So I'm using generalized linear model and showing here partial effects plots to remove the effects of the seasonality, remove the effects of the warming temperature and the temperature trends, both seasonal and long term, and to remove the effects of variable salinity. And what I'm showing in the first plot A here is the trend in fugacity of CO2 as a deviation from the mean after removal of the warming and the salinity effects and the seasonal effects. And so the trend we're seeing up there is still significant. It's slightly weaker than for the more data, but it's still about 1.3 parts per million per year. And the decadal trend is the best predictor for all the changes that are happening. The monthly differences are significant. Temperature is obviously a very, very strong factor as well, and salinity effects are very weak. Some people are temperature correcting fugacity of CO2 before doing this analysis. I can do that as well, but the decadal trend is still remaining very strongly significant. In the remaining talks, I'm showing the raw data of FCO2 rather than temperature corrected ones, because there are slight overcorrections of the data by the algorithm, which has been not exactly fine-tuned for the GBR. Okay, so that's the southern GBR. At the Yangala station, again, air CO2 is going up as expected, with red values in summer and black in winter again. Again, the data are from 2009 to 2019. And what we measure here is not CO2, but dissolved inorganic carbon at the second plot, and aragonite saturations, total alkalinity, that's the third plot here. In all cases, we're seeing upward trends, but the total alkalinity is not significant. So from those two seawater carbonate values, we can then calculate FCO2 to make the data comparable with the Heron Island station. We can calculate pH, and we're using also temperature and salinity as input variables. So pH is significantly declining in these 10 years alone. FCO2 is significantly increasing in these 10 years. Again, partial effects plots and generalized linear models show significant increases in dissolved inorganic carbon, in fugacity of CO2, significant declines in pH, declines in aragonite saturation state, and the Revell factor, which is significantly increasing. Total alkalinity is not changing significantly. So again, these trends are slightly weaker than in the raw data, but very, very strong nevertheless. Now, 10 years of data is not a lot, and many places around the world have had decadal analysis done by now, and typically have not found significant changes. On the GBR, there are significant. What does it mean? It means, first of all, the water in the GBR is very much forced by atmospheric values. Second, we only have relatively short time series, but we are privileged to have the time series from Hawaii about atmospheric CO2 from the Mauna Loa station, but data going back to 1958. So that's the seasonal changes which are characteristic for the Northern Hemisphere. And the CO2 values at Ames or at Cape Ferguson is tracking exactly the Hawaiian values as well. On top of that, the red values are the seawater values with a significant trend plotted over it over those 10 years. And again, these slopes are not significantly different from the atmospheric values. But what I'm showing here is that the lowest values that we are seeing today are really very much in the range or even slightly above the highest values we would have seen in the 1960s. So the whole seawater chemistry, despite its huge fluctuations in these coastal waters, have now exited the envelope that the reef would have seen in the 1960s, which is of real concern. So we've documented a 60% increase in 10 years. And if the trend has followed the atmospheric trend, which is very, very likely over the last 60 years, we have seen a 28% increase in 60 years, and probably a greater than 30% change overall in the GBR since pre-industrial times. The estimates are conservative because the Revell factor has been increasing, and the fluctuations in the past, Revell factor is basically a measure of the buffer capacity of the seawater. So the fluctuations would have been most likely less in the 1960s. That means the maxima would have been lower than they are today. And pretty much the same is happening at the Heron Island station as well. Here we have not quite exited the envelope, but we're in the very upper limit of what the seawater would have seen in the 1960s. Now, we only have data from 2 stations. The Great Barrier Reef is 2,500 kilometers long. These stations may or may not representative of the whole GBR. Again, e-reefs through the RECOM model shows how hugely variable CO2 actually can be, or in this case, it's alkalinity. So we can't be sure at this stage whether these long-term trends are representative for the whole GBR. And similarly, Kelly Hannon and the whole Filmandi group, together with many other people, have shown smaller scale variability near the reef that are experienced on top of the seasonal changes, on top of the dial changes that I've just shown you from the seawater itself further away from the reef. Like these changes that Kelly has shown here are from within 10 centimeters in the boundary layer of the reef. And if you're going into the sediments, you're seeing even greater changes. So the closer you go to the reef, the more the benthic processes are dominating. But nevertheless, the reef is still experiencing a condition that is forced by the atmosphere and that is changing very, very rapidly. So yes, we've got very few data from the GBR. There's significant spatial and temporal variability data. The e-reefs model is getting there in showing some of the spatial trends and also some of the temporal variability. And overall, the similarity of the trends I've shown you from Heron Island and Nyungala to the atmospheric trends, the similarity of the trends at both stations to trends from other stations that are from oceanic regions, both really confirm it's not just a concern for those 2 places, but probably for many, many other places in the GBR even today. Now, I'm a biologist, not a seawater chemist. So what I was really interested in, what does it matter to the reef? So I've spent the last 10 years doing a number of expeditions with 40 amazing collaborators from all around the world at CO2 seeps in Papua New Guinea, where volcanic gases that are almost pure in CO2 are exiting the seafloor, and they're providing spatial gradients in CO2 that cannot be simulated in lab experiments because these gradients have existed for hundreds of years, maybe thousands of years, we don't know. But we've got cores from these massive varieties. We know they've existed for at least hundreds of years. Now that study has been incredibly fruitful. I think we've published close to 50 publications, and we looked at all sorts of biological properties of reefs and seagrasses, microbial communities, planktons, and a lot of reef organisms are changing very, very steeply along those CO2 gradients. You get more seagrass because the higher CO2 facilitates plant growth. You obviously get less compromised types of corals, in particular the branching corals, and so on. I'm not going into details here. I'm just picking 3 case studies that came from those investigations of the benthos along gradients of CO2. So in this case, I'm plotting aragonite saturation state from high on the right to low on the left. And I've been looking at small scale changes of coralline algae, of fleshy macroalgae, and of densities of coral juveniles along those gradients. And consistently across the 3 seeps that we've got, coralline algae are steeply declining along those gradients, macroalgae are steeply increasing, and coral recruitment are declining along those CO2 gradients. So these data were fairly consistent across the data sets, and the macroalgae and coralline algae are also consistent with observations from other CO2 seeps around the world. So we took those data and used them to ask, do we find the same spatial changes in the Great Barrier Reef as well? Because from the e-reefs model, you've seen there are spatial gradients, and like in the seeps, we are using space for time substitution and basically are using it to predict what would happen in the future if the seawater chemistry is changing. We are using spatial gradients to make predictions into the future. On the Great Barrier Reef, spatial gradients already exist as well. And so we picked 2 long-term monitoring data sets for those 3 responses: crusted coralline algae, macroalgae, and latitudinal densities. One data set was the combination of the AIMS long-term monitoring data from offshore reefs together with the marine monitoring data from the inshore reefs. These are those gray dots in the bottom left plot of the reef. And the second data set was rapid ecological assessments. Swim surveys I had been conducting a few years earlier, where we've been basically swimming up and down the Great Barrier Reef and doing visual surveys on 160 reefs at depths between this reef flat and 18 meters depths, both fronts and backs. So really all around the reef. And these are reef averaged values that I'm showing you. So those 2 data sets existed for coralline algae and macroalgae, and the third set existed for lesser data existed for coral tubular densities, but we used what we had and got some decent spatial representation. And Matthew Mongin and his team calculated aragonite saturation state as a long-term means for each of those data points we had. And that's work spearheaded by Joy Smith, who did a postdoc with us and looked at that issue. And you can see very steep changes in aragonite saturation state, with yellow indicating high values and purple indicating low values. We also used suspended fine sediments, temperature, and chlorophyll salinity as additional predictors. And basically, so we threw these 6 data sets together to large-scale monitoring for 3 responses, together with these response data, and basically interrogated the data. Are we finding responses of these key indicators for responses to ocean acidification on the GBR today? And the answer is a resounding yes, unfortunately. So, for example, here, these are the crusted coralline algae data from the long-term data monitoring data set. Aragonite was the greatest predictor, the strongest predictor for CCA cover. Fine sediments were also important. And I need to say we ran 2 different models. We used aggregated boosted trees, and these what I'm showing here is partial dependency plots. So we've used an environmental model where all the environmental predictors were included together with aragonite saturation state. And so these are partial effects, and the relative influence of aragonite is in this case 90%, and fine sediments about 7%. The other factors were much less important. We also run spatial models where we at the distance across the Great Barrier Reef, along the Great Barrier Reef, and aragonite saturation state competing. And yes, as we all know, there are fewer coralline algae inshore than offshore, but even after we are removing these natural gradients across the shelf, we're finding very significant effects of aragonite saturation state above and beyond these cross-shelf patterns. So at the same distance across the shelf, if CO2 is higher, we're finding less CO2, less coralline algae than if CO2 is lower. So Joy repeated this for all these 6 response types, 3 data sets and 2 data sets and 3 responses. And that's a summary graph that plots all the results together, not showing the additional environmental predictors again. But the red lines are the rapid ecological assessments, and the green ones are the long-term monitoring data. In all cases, the direction of response are as predicted, and the size of the response for the macroalgae and for the coralline algae is really literally a 2-fold change. The coralline algae are halving in cover, as CO2 goes up, again, once it's corrected for spatial patterns and for additional sediments and so on, macroalgae are doubling as CO2 goes up, and coral juvenile densities are declining by about 15% in both data sets. So GBR-wide aragonite saturation state is a strong predictor for changes in all three groups in these two independent data sets. And in all three data sets, I mean, there's a lot of noise, and the coral juvenile data are very sparse. But overall, there seems to be a threshold at a long-term mean aragonite saturation state of about 3.5-ish. But in most of the models, fine sediments were also important and acted in the same direction as CO2. That means these were additive effects. That means there was some CO2 additionally to the fine sediments. The effects were even more severe on coralline, algae, macroalgae, and juvenile densities. So we can show that aragonite saturation state is a really important predictor for these three measures, and which are arguably in a context of changing climate, of warming and higher disturbance frequencies from warming times with bleaching events and mountain cyclones in particular. We need the coral juveniles to help the reefs recover. We don't need the macroalgae because we know they're slowing the recovery. And we need the Costas coralline algae because they're key facilitators for coral recovery as well. So the areas of highest risk, if these thresholds of 3.5 are true, are mostly inshore along the GBR and in the southern Great Barrier Reef. According to the reefs data, again, we really need some more data from mapping and monitoring in the GBR to validate further, but these patterns do make sense, and they're also quite similar to what we've measured at Ingala. At Ingala, we measured a mean aragonite saturation state of 3.56 on an annual basis. Summer values were about 3.7, winter were about 3.5. So some inshore reefs and some southern reefs probably are, because calcification is such a strong function of aragonite saturation state, may or may not be calcifying on an annual basis any longer. But certainly GBR-wide, aragonite is quite low in the 6 winter months. GBR-wide, it's below 3.5, which obviously has significant implications for these responses. The predicted rate of change is presently a drop in aragonite by 0.1 units every 14 years. So in less than a quarter of a century, just before 2050, we'll be reaching values which are really already starting being quite critical for the GBR. And under Paris 2 degrees agreement, aragonite would drop to about 2.7 GBR-wide, which is really very bad news. So it's on its own without the climate change and bleaching effects. It is a factor we need to consider more in our outlook about the Great Barrier Reef. So just in summary, our data very strongly suggest atmospheric forcing of CO2 in the GBR. We're clearly showing ocean acidification is not a future concern. So many people are saying, well, OA is something that we need to worry about in the future. It is creeping, it is silent, it is not visible like bleaching, but if CO2 has increased by greater than 30%, that's faster than any other nutrient changes in the water, and it is likely affecting the GBR today. So CO2 is a plant nutrient, so it is more comparable. The whole process is really more akin to a water quality issue than a climate change issue. And as you know, the current rate of change is 10 times faster than it's any time in the last 300 million years. And rates of change are obviously a key feature for capacity to adapt to change. But what is also really important to consider is that rate changes are irreversible at timescales of thousands of years. And there's no latitudinal escape. For warming, at least terrestrial ecosystems, and some are showing some signs of shifting towards the higher latitudes. You haven't got that option for aragonite. It is a global issue and it's happening everywhere. So there's no escape into the latitude because of the temperature gradients. Now, the Sustainable Development Goal 14 is listing ocean acidification as part of prevention of marine pollution. But I'm arguing that, and furthermore, cumulative effects between ocean acidification and sediments and nutrients and ocean acidification and climate change are something we are really concerned about. We are pretty certain from estuarine studies that there are significant interactions between nutrients and OA, because if you've got higher nutrients, we typically have higher turbidity, therefore less light, and therefore the shift between photosynthesis and respiration shifts more towards respiration, therefore you get more CO2. And as I've shown you, climate change is also making the health of coralline algae and of coral recruitment really critical. So we are getting some synergistic effects here in the two functions. So if there was means to slow coastal acidification along the GBR, that would go through the slowing of nutrient pollution. If we are concerned about the cumulative effects of OA and sedimentation, we can change the sedimentation rates through water quality management, and that would also help releasing the pressure on the GBR under a global change in ocean acidification. But overall, what I really strongly argue is we need to start thinking about OA in its own term, in terms of management responses. Typically, OA is just used as a stack on in terms of management as climate change and ocean acidification. It is a property, it is a response on its own. Yes, it's got the same cause as CO2, but it's really affecting different regions. It's worse in winter than in summer, and different organisms are at highest risk. Chronic exposure leads to shift in GBR communities, as we've shown. And it also deserves mentioning because OA is less politicized than climate change, and it is pure physics, pure chemistry. So it's much easier at this stage to communicate in these politicized times with climate change. That doesn't mean we don't need to talk about climate change, but it is an additional topic to take on its origin. So I think a lot of collaborators, this work is a first look, it's 3 studies which we all published this year, but it really builds on the effort and the work of so many people, and I'm listing only a few here. I'm greatly thankful to IMOS, the Integrated Marine Observing System, for maintaining these data streams that are so valuable. The AIMS long-term monitoring program, which has been monitoring reefs now for 30 years and providing these data, and a whole heap of other people who have contributed to this work. So thank you for listening, and I'm happy to answer questions.